Right now, you are moving through space at 600 kilometers per second. Not because Earth spins, not because Earth orbits the Sun, because your entire galaxy is traveling, carrying you, carrying the Sun, carrying 200 billion stars, all moving together through the void. You live in the Milky Way, a spiral galaxy 100,000 light-years across. So large that light takes 100,000 years to cross from edge to edge. And this galaxy is just one of 2 trillion galaxies in the observable universe. If you enjoy these peaceful explorations of the cosmos, I would love for you to subscribe. Join this community finding calm in the vastness of space. Leave a comment about where you are in the world. What time is it there? Do you ever look up at the night sky and think about galaxies? I love knowing we are scattered across the planet, all finding rest in cosmic wonders together. A galaxy is an island of stars, held together by gravity, separated from other galaxies by mostly empty space. The nearest major galaxy to the Milky Way is Andromeda, 2.5 million light-years away. Light from Andromeda takes 2.5 million years to reach your eyes. When you look at that galaxy, you see it as it was before humans existed, before our species evolved. You are looking into deep time, seeing ancient light. Galaxies come in shapes, spiral galaxies like the Milky Way, arms of stars rotating around a bright center, elliptical galaxies, smooth spheres or ovals of old stars, irregular galaxies, chaotic clouds with no clear structure. The Milky Way has 4 major spiral arms: stars, gas, and dust arranged in sweeping curves. The arms rotate, but not like a solid wheel. Stars move through the arms. The pattern persists while individual stars come and go. Our Sun sits in a minor arm, about halfway out from the galactic center, 26,000 light-years from the core. We orbit the center once every 230 million years, 1 galactic year. The last time Earth was in this position, dinosaurs had not yet evolved. Reptiles were just beginning to dominate. The Sun has orbited the galaxy only 20 times since it formed. We are young in galactic terms. At the center of the Milky Way is a supermassive black hole, 4 million times the Sun's mass, called Sagittarius, a star. Everything in the galaxy orbits this central mass. The black hole itself is invisible, but we see stars orbiting it, moving at incredible speeds, whipping around the center in tight ellipses. This revealed the black hole's presence, its tremendous gravity. Galaxies are mostly empty space. If you shrank the Milky Way to the size of North America, stars would be grains of sand separated by kilometers. Vast emptiness between tiny points of light. But galaxies are not static. They evolve. Stars form from gas clouds, live their lives, die, return their material to space. New stars form from the debris, recycling. Generations of stars building on what came before. Heavy elements in your body were made in stars: carbon, oxygen, iron, calcium, all forged in stellar cores, released when stars died, scattered through the galaxy, eventually incorporated into Earth, into you. You are made of star material, ancient atoms that have existed since those early stellar deaths, recycled through the galaxy, through countless processes, now arranged into your form, temporarily. Galaxies also collide, despite the emptiness inside them. Andromeda is approaching the Milky Way. In 4 billion years, they will merge, become one larger galaxy. The collision will be gentle. Stars are so far apart, they will mostly pass between each other. But gravity will reshape both galaxies. pull them into new forms, create bursts of star formation as gas clouds compress. Our sun will likely survive unchanged, flung to a different orbit perhaps, but intact. The night sky will look different, Andromeda's stars mixing with ours, two galaxies becoming one. This is common in the universe. Galaxies merge constantly. The Milky Way has absorbed smaller galaxies already. Streams of stars in our outer regions are remnants. Consumed galaxies torn apart and incorporated. Everything moves. Galaxies rotate, orbit each other, collide, merge, all driven by gravity, the force that holds everything together, that creates structure in the universe. Tonight, when you look up, remember you are inside a galaxy, one of trillions, a vast rotating island of stars, moving through space, evolving, changing, ancient and ongoing. The light you see from distant stars left them years ago, decades ago, centuries ago. You see the galaxy's past, never its present. Light speed limits what you can know, and in this vastness there is peace. You are part of something immense, something ancient, something that will continue long after you, the galaxy that carries you, through space, through time, always moving, always here. Galaxies move through space now, but where did they come from? How did islands of stars form in empty space? The universe began 13.8 billion years ago. The Big Bang, not an explosion in space, an expansion of space itself. Everything emerging from a single point. At first, there were no galaxies, no stars, just energy, pure radiation. The universe was too hot for matter to exist. Only after 380,000 years did it cool enough for atoms to form. Hydrogen atoms, mostly. Some helium, the simplest elements. These atoms filled space uniformly, almost uniformly. Tiny variations existed. Regions slightly denser than others, barely noticeable, but enough. Gravity amplified these small differences. Denser regions attracted more matter, became denser still, attracted even more. A feedback loop, small irregularities growing into massive structures. The first stars formed about 100 million years after the Big Bang, in the densest regions, clouds of hydrogen collapsing under their own gravity, heating up, igniting fusion, becoming stars. These first stars were enormous, hundreds of times the sun's mass. They burned bright and fast, lived only a few million years, then exploded, scattering heavy elements into space. These explosions enriched the hydrogen gas, added carbon, oxygen, iron, elements that did not exist before. The next generation of stars formed from this enriched gas, smaller, longer-lived, more like the sun. Stars clustered together, thousands, millions, held by gravity. These clusters merged, combined, grew into the first galaxies. Small, irregular galaxies. Nothing like the elegant spirals we see today. Early galaxies were violent, stars forming rapidly, supernovae exploding constantly, gas swirling chaotically, everything turbulent, active, raw. Over billions of years, galaxies organized. Random motion settled into rotation. Gas flattened into disks. Spiral arms emerged. Order from chaos. Gravity shaping matter into patterns. Not all galaxies became spirals. Some merged early, became elliptical. Their stars scattered in all directions. No disk, no arms, just spheres or ovals of old stars. The Milky Way formed about 13 billion years ago, assembled from smaller galaxies merging, growing. The process took billions of years, is still happening. We continue absorbing smaller galaxies. Dark matter played a crucial role. This invisible material outweighs normal matter 5 to 1. creates gravitational scaffolding. Galaxies form in dark matter halos. The visible matter we see is just the surface. Without dark matter, galaxies would not exist. Not enough gravity to hold them together. Stars would fly apart. The rotation would tear galaxies apart. But dark matter provides the mass, the gravitational anchor. We cannot see dark matter, cannot detect it directly, but we see its effects. Galaxies rotate too fast for their visible mass. Something invisible holds them together, provides extra gravity. Galaxy formation is not finished. New galaxies still form, mostly small ones now. The era of giant galaxy formation has passed, but the process continues, will continue for billions of years. Each galaxy has its own history, its own formation story. Some formed early, some late, some merged often, some stayed isolated. The variety is immense. The Milky Way's history is written in its stars. Old stars in the halo formed first, ancient, metal poor. Stars in the disk formed later, enriched with heavy elements. The younger stars in the spiral arms. You can read a galaxy's age by looking at its stars. Blue stars are young, hot, massive. Red stars are old, cool, long-lived. The color mix reveals the galaxy's timeline. Galaxies are still evolving, still forming stars, still merging. The universe, at 13.8 billion years old, is still young, still changing, still creating new structures. The galaxies you see tonight are snapshots, moments in ongoing lives. They were different billions of years ago, will be different billions of years from now. Everything temporary, everything changing, but the process is slow. Galactic time operates on scales incomprehensible to human life. Stars live millions or billions of years. Galaxies evolve over billions. To us, they seem eternal, unchanging, but they are not. They are just slow. Tonight, those ancient galaxies shine. Light from their formation still traveling, reaching your eyes, telling stories of the early universe, of how everything began, of how stars and galaxies emerged from simplicity, creating the cosmos we see. Galaxies formed over billions of years. Some became spirals. These are the most beautiful, the most organized. The Milky Way is one. Spiral galaxies have three main parts: a central bulge, a flat disk, and a halo surrounding everything. The bulge is the bright center, densely packed with old stars, mostly red and yellow. These stars formed early in the galaxy's history. They orbit in random directions, creating a sphere. The disk extends outward from the bulge, flattened by rotation, like pizza dough spinning in air. Centrifugal force balances gravity, creates a thin plane where most stars orbit. The spiral arms are not solid. They are density waves, regions where stars and gas bunch up temporarily. Think of traffic on a highway. Cars bunch in certain areas, create slow spots, but individual cars move through. The jam persists while cars change. Spiral arms work the same way. Stars move through the arms, spend time in them, then leave. But the arm pattern remains, rotating slowly around the galactic center. The arms are where star formation happens. Gas clouds enter the density wave, get compressed, collapse, form new stars. These young blue stars make the arms bright, make them visible. Between the arms, fewer stars form. Older yellow and red stars dominate. Less gas, less compression, quieter regions. The Milky Way has four major arms: the Perseus arm, the Sagittarius arm, the Norma arm, the Scutum Centaurus arm. Our Sun sits between Perseus and Sagittarius, in a minor structure called the Orion Spur. From inside, We cannot see the full spiral pattern. We are embedded in the disk, like trying to see a forest from inside it. We must infer the structure from observations. The disk also contains dust, tiny particles of carbon and silicates, created in dying stars, scattered through space. This dust blocks light, makes distant parts of the galaxy invisible. The galactic plane is dark with dust. Looking toward the center, we see only a few thousand light years. Then dust obscures everything. Infrared light penetrates dust better. Infrared telescopes reveal what visible light cannot. The halo surrounds the disk, a sphere of old stars and globular clusters. These stars orbit in all directions, not confined to the disk. They are ancient, formed when the galaxy was young, before it flattened. The halo also contains dark matter, invisible, undetectable except through gravity. This dark matter extends far beyond the visible galaxy, creates a massive gravitational well, holds everything together. Without the halo's dark matter, the disk would fly apart. Stars orbit too fast. Visible matter alone provides insufficient gravity. Something invisible anchors the system, keeps it stable. Spiral galaxies rotate, but not like solid objects. The inner regions orbit faster than outer regions. Differential rotation. This would wind the arms tighter over time. But they do not wind up. The density wave pattern persists. The rotation curve reveals dark matter. Plot orbital speed versus distance from center. For visible matter alone, speed should decrease outward, but it stays constant, flat. This flatness requires invisible mass. Dark matter in the halo. Some spirals have bars, elongated structures through their centers. The Milky Way has a bar. Stars orbit in elongated paths, creating this linear feature. About half of spirals are barred. Bars channel gas toward the center. Feed star formation. Feed the central black hole. They are dynamic features. Form, dissolve, reform, changing over hundreds of millions of years. Spiral galaxies are factories, creating new stars. Recycling material. Gas collapses into stars. Stars live, die, return gas to space. Enriched with heavy elements, this gas forms new stars. The cycle continues. Our sun is a product of this cycle. Third or fourth generation star, made from recycled material, from stars that died before the sun formed. Each generation enriching the galaxy, building complexity. Right now, the Milky Way's spiral arms rotate. Stars move through them. Gas compresses. New stars ignite. All in elegant patterns, repeating, ongoing. The spiral structure that has existed for billions of years will exist for billions more. Spiral galaxies have structure, order, but not all galaxies are spirals. Some are elliptical, smooth, featureless, ancient. Elliptical galaxies are spheres or ovals of stars. No disk, no spiral arms, no organized rotation. Stars orbit in all directions. Random paths, creating a three-dimensional swarm. They range in size dramatically. Dwarf ellipticals contain a few million stars. Giant ellipticals contain trillions. The largest galaxies in the universe are ellipticals, monsters at the centers of galaxy clusters. Most ellipticals are red. Their stars are old, red giants and red dwarfs. Very few young blue stars. Little gas remains to form new stars. Star formation stopped billions of years ago. Ellipticals form through mergers. When galaxies collide and combine, the collision scrambles their structures, destroys the orderly disks, mixes stars into random orbits. The result is elliptical. The Milky Way will become elliptical when it merges with Andromeda in 4 billion years. The collision will destroy both spiral structures. create one large elliptical galaxy. Astronomers call it Milkomeda. In galaxy clusters, ellipticals dominate. The central massive galaxies are always elliptical. They formed by consuming other galaxies, growing through mergers, becoming giants. These giant ellipticals can be 10 times larger than the Milky Way, contain 10 times more stars, truly immense. They sit at gravitational centers, eating smaller galaxies that wander too close. Ellipticals contain little dust, little gas. Most was used to make stars long ago, or blown away by stellar winds and supernovae. What remains is mostly stars and dark matter, lots of dark matter. The largest ellipticals have extensive halos, dark matter extending far beyond the visible stars. These halos can be 10 times wider than the galaxy itself. Invisible scaffolding holding everything together. Some ellipticals are boxy, others are elongated like cigars. The shapes depend on star orbits, which directions stars prefer. Box-like shapes from radial orbits, cigar shapes from circular orbits in random planes. At their centers, ellipticals host supermassive black holes, larger than those in spirals, billions of solar masses. The biggest black holes exist in giant ellipticals, some over 10 billion times the Sun's mass. These central black holes are usually quiet now. Little gas remains to feed them, but they were active in the past. Quasars, blazing with energy, outshining their entire galaxies. Those days are over. Now they sleep. Ellipticals look simple, smooth distributions of stars, but structure hides within. Shells, ripples, tidal streams, remnants of consumed galaxies, evidence of past mergers written in star positions. Advanced imaging reveals these features. Faint arcs of stars, concentric shells around the galaxy. Each shell is debris, a small galaxy torn apart, its stars scattered, gradually mixing into the larger galaxy. Some ellipticals rotate, not like spirals, but measurable rotation. Others do not rotate at all, stars moving too randomly, no net angular momentum. These non-rotating ellipticals formed from head-on mergers. Star ages in ellipticals span a range. Most stars are old, 10 billion years or more, but some are younger, formed recently from remaining gas, or brought in by accreted galaxies. Colors vary slightly. Redder ellipticals have exclusively old stars. Yellower ones have some younger populations. Metal content affects color too. More metals mean redder stars. Ellipticals are endpoints, final forms. Spirals can become ellipticals through mergers, but ellipticals rarely become spirals. Too much energy lost, too much structure destroyed. The transformation goes one way. In the distant future, most galaxies will be elliptical. As mergers continue, as spiral galaxies collide and combine, the universe will fill with smooth red ellipsoids. Star formation mostly finished. But this takes time. Tens of billions of years. More time than has passed since the Big Bang. The universe is still young, still dynamic. Spirals still dominate in many regions. Elliptical galaxies are peaceful. No active star formation, no supernovae disrupting things. Just old stars quietly orbiting, slowly evolving, slowly fading as their stars age and die. Right now, these smooth galaxies drift, ancient, quiet, full of old red stars, living out their final billions of years, unchanging, eternal seeming, the universe's oldest residents, holding memories of the early cosmos, when everything was younger, more violent, more alive. Ellipticals are ancient and quiet, but at their centers, something powerful waits. The same is true for spirals. At every galaxy's heart sits a supermassive black hole. The Milky Way's black hole is called Sagittarius, a star, 4 million times the Sun's mass, compressed into a region smaller than Mercury's orbit, enormous mass in tiny space. We cannot see the black hole itself. Black holes emit no light, but we see its effects. Stars orbit it, moving at tremendous speeds, whipping around the center in years or decades. One star, called S2, orbits in 16 years, gets as close as 17 light hours from the black hole, moves at 5,000 kilometers per second, 3% the speed of light. This speed reveals the central mass. By tracking these stars over decades, astronomers calculated the black hole's mass precisely, watched stars accelerate as they approached, slow as they receded, perfect Keplerian orbits around an invisible point. In 2020, astronomers imaged Sagittarius, a star, directly. Not the black hole, but the glowing gas around it. The accretion disk, hot material spiraling inward, heating up, radiating before crossing the event horizon. The image showed a ring, dark center where the black hole sits, bright ring of gas surrounding it. The gas orbits at nearly light speed, heated to billions of degrees, glowing in radio waves. This black hole is quiet now. Little material falls in. It grows slowly. Occasionally, a gas cloud wanders too close, gets shredded, produces a flare of radiation, but mostly it waits, dormant. Other galaxies have more active black holes, fed by steady streams of gas. These active galactic nuclei outshine their entire galaxies. Quasars, blazars, Seyfert galaxies, all powered by supermassive black holes feeding. The most luminous quasars shine with the light of 1 trillion suns. From a region the size of the solar system, all that energy from matter falling into a black hole, converting mass to energy with perfect efficiency. As matter spirals in, it forms an accretion disk. Friction heats the disk. The innermost regions reach millions of degrees, radiate X-rays. Further out, thousands of degrees, radiating visible light. The disk glows. Jets sometimes form, perpendicular to the disk. Matter accelerated to nearly light speed, shot outward in tight beams. These jets extend thousands of light years, plowing through the galaxy, through intergalactic space. The jets are magnetic. Twisted magnetic fields accelerate charged particles, focus them, direct them outward. The particles radiate as they spiral along field lines, creating the jet's glow. Every large galaxy has a central black hole. The mass correlates with the galaxy's mass. Bigger galaxies have bigger black holes. The ratio is remarkably consistent, about 1% of the central bulge's mass. This suggests black holes and galaxies grow together, co-evolve. The black hole influences star formation. Its jets blow gas out of the galaxy, stop new stars from forming, regulate growth. Without central black holes, galaxies would be different. More gas, more star formation, different structures. The black holes shape their host galaxies, control their evolution. Supermassive black holes likely formed early, perhaps from the collapse of massive gas clouds in the early universe, or from the merger of many smaller black holes. The process is still debated. Once formed, they grow by eating gas, stars, other black holes, anything that comes too close. Over billions of years, they accumulate mass, grow to millions or billions of solar masses. When galaxies merge, their black holes eventually merge too. First, they orbit each other, spiraling inward, taking millions of years. Finally, they collide, combine, create a larger black hole, release gravitational waves. We have detected these gravitational waves. ripples in space-time from merging black holes, mostly stellar mass black holes. But eventually, we will detect supermassive mergers. When our detectors become sensitive enough, the galactic center is violent. Radiation, magnetic fields, relativistic particles, but also strangely stable. The black hole has been there for billions of years, will be there for billions more, a permanent fixture, an anchor. Right now, Sagittarius. A star sits at the Milky Way's heart, waiting, growing slowly, pulling stars into tight orbits around it. The gravitational center of everything. The point around which 200 billion stars revolve. Silent, invisible, immensely powerful. Black holes sit at galactic centers, but most of the galaxy is star nurseries, regions where new stars are born. This happens in molecular clouds. Molecular clouds are cold, 10 to 20 Kelvin, just above absolute zero, made mostly of hydrogen molecules, plus dust, carbon monoxide, other simple molecules. These clouds are dense. For space, about 1,000 molecules per cubic centimeter, still far more empty than any vacuum we can create, but dense enough for gravity to matter. When a cloud region becomes dense enough, it collapses. Gravity pulls it inward, the cloud fragments, each fragment collapsing separately, each becoming a star. As the fragment collapses, it heats up. Gravitational energy converts to thermal energy. The center gets hotter, denser, eventually hot enough for fusion. Hydrogen fuses to helium. A star is born. This process takes millions of years, from initial collapse to ignition. But once started, the star will burn for millions or billions of years, depending on its mass. Massive stars burn hot and fast, live only a few million years, explode as supernovae, return their material to space, enrich the cloud with heavy elements. Small stars burn cool and slow, live trillions of years, longer than the current age of the universe. No small star has ever died naturally. They all still burn. Star formation happens in spiral arms, where gas gets compressed. The density wave squeezes molecular clouds, triggers collapse, creates clusters of new stars. These young stars are blue, hot, massive. They light up the spiral arms, make them bright and visible. Without star formation, spiral arms would be invisible, just slight density variations. The Milky Way makes about 1 solar mass of new stars per year. This seems like a lot, but spread across the whole galaxy, it is sparse. Most regions are quiet. Occasionally, a cloud collapses, briefly active, then quiet again. Some galaxies form stars much faster, starburst galaxies, creating hundreds of solar masses per year, usually triggered by galaxy interactions. Collisions compressing gas, triggering massive star formation. Star formation creates structure, illuminates the galaxy, but also regulates itself. Massive stars produce stellar winds, radiation pressure. These push gas away, disrupt nearby clouds, stop formation nearby. Supernovae do the same. Shock waves from explosions compress some gas, trigger star formation, but also blow gas away, heat it, make it too hot to collapse. This feedback limits star formation, prevents all the gas from turning into stars at once, stretches the process over billions of years. In elliptical galaxies, star formation has stopped. The gas was used up or blown away. What remains is too hot, too dispersed, cannot collapse. These galaxies are retired, living on past star formation. But spirals continue. Gas falls inward from the halo, from intergalactic space, replenishes what was used, keeps the process going. The Milky Way has fuel for billions of years more. Eventually, this will end. the gas will run out, star formation will stop, the Milky Way will fade, become redder as blue stars die. Eventually, only red dwarfs remain, the last stars, burning for trillions of years. But this is distant future. Now, star formation continues, in the arms, in molecular clouds, creating the next generation, building on what came before. Right now, somewhere in the Milky Way, a cloud collapses, forms new stars, blue giants igniting, beginning their brief brilliant lives, the galaxy renewing itself, as it has for billions of years, as it will for billions more. Tidal forces distort large galaxies, but what about small ones? Dwarf galaxies, the universe's most common type. Dwarf galaxies contain a few million to a few billion stars, small compared to the Milky Way's 200 billion. But they outnumber large galaxies 10 to 1. Most dwarfs are irregular, no organized structure, no spiral arms, no smooth elliptical shape, just random clouds of stars and gas. Chaotic, simple. The Magellanic Clouds are irregular dwarfs, visible from Earth's southern hemisphere, companions to the Milky Way. Eventually, they will be consumed, absorbed into our galaxy. Dwarf ellipticals are smooth, like miniature versions of giant ellipticals. Old stars, no gas, no star formation, quiet, ancient, often found in galaxy clusters. Dwarf spheroidals are even smaller, fainter, so faint they are nearly invisible, only discovered recently. Extremely low surface brightness, more dark matter than stars. These ultra-faint dwarfs challenge detection. A few thousand stars spread across large volumes. Individual stars barely brighter than background. Special surveys find them. Statistical analysis revealing their presence. Why care about dwarfs? They are common. Most galaxies are dwarfs. Understanding them means understanding typical galaxies, not the spectacular spirals. The ordinary majority. Dwarfs also reveal dark matter. They have the highest dark matter fractions. Some are 99% dark matter, 1% stars, almost entirely invisible mass. This makes them ideal dark matter laboratories. Studying how stars move in dwarfs reveals dark matter distributions, how dark matter clumps, how it interacts with normal matter, or does not interact. The smallest galaxies teach us about the universe's majority component. Dwarf galaxies also preserve ancient chemical signatures. Low mass means less recycling, less star formation. Stars formed early, from primordial gas. Their compositions reveal the early universe. The first stars formed in dwarf-sized dark matter halos, before large galaxies existed. Dwarfs might be fossils from that era, surviving unchanged. Time capsules from cosmic dawn. Some dwarfs are satellites, orbiting large galaxies like the Milky Way. These satellites are common. Each large galaxy has dozens, perhaps hundreds, most undiscovered, too faint to see. The satellite count tests dark matter models. Simulations predict thousands of dark matter halos around large galaxies. But we see only dozens of satellite galaxies. Either most halos have no stars, or dark matter is different than predicted. Field dwarfs are isolated, not satellites, not in clusters, alone in voids. These dwarfs formed in isolation, evolved slowly, undisturbed. They represent pristine galaxy evolution. Blue compact dwarfs are active, bursts of star formation, bright blue stars. Despite low mass, these bursts are triggered by gas infall, or dwarf-dwarf mergers, brief intense activity. Dwarf galaxies can merge with each other, create larger dwarfs, or occasionally create spirals. Over billions of years, small galaxies combining, building larger structures. this bottom-up growth. The Milky Way likely formed this way, many small galaxies merging, growing, eventually becoming the large spiral we see. Dwarfs are building blocks, the fundamental units. Tidal dwarfs form from collisions. When large galaxies merge, tidal tails pull out. Material in these tails can collapse, form new dwarf galaxies, born from debris, short-lived, eventually absorbed. Dwarf galaxies host small black holes, intermediate mass, hundreds to thousands of solar masses, too small for supermassive, too large for stellar. These intermediate black holes are rare. Dwarfs might be where to find them. Understanding dwarfs completes galaxy knowledge, not just the giants, the full population, from smallest to largest, all part of the cosmic ecosystem. Right now, dwarf galaxies drift everywhere, in clusters, around large galaxies, in voids, mostly invisible, faint but numerous, the majority, the universe's most common galaxy type. Small but essential parts of cosmic structure. Stars form in molecular clouds, often in groups, star clusters. Some clusters are loose, open clusters, a few hundred stars. These disperse over time, scatter into the galaxy. Other clusters are permanent, globular clusters, hundreds of thousands of stars, packed tight, held together by gravity. These last forever. Globular clusters orbit in the galactic halo, high above and below the disk, in long elliptical orbits, plunging through the disk, emerging on the other side, repeating. The Milky Way has about 150 known globular clusters, probably more undiscovered, hidden behind dust, or too faint to detect. Each cluster is ancient, 10 to 13 billion years old, formed when the galaxy was young, before the disk formed, when everything was more chaotic. The stars are all old, red giants and red dwarfs. No blue stars, no young stars. Star formation stopped billions of years ago. All the gas was used up or ejected. Globular clusters are beautiful, spheres of stars, densest at the center, thinning outward. At the core, stars are separated by light days, incredibly close for stars. In the solar neighborhood, stars are light years apart. This density creates interactions. Stars pass close to each other. Gravitational tugs alter orbits. Sometimes stars collide, merge, form blue stragglers, stars that look younger than they should. Blue stragglers are created by mergers, two old stars combining, creating more mass, more heat, burning hotter, appearing younger. These stars are markers of past collisions. Globular clusters also contain exotic objects, X-ray binaries, millisecond pulsars, neutron stars orbiting normal stars, created through interactions, close encounters, captures. The oldest globular clusters are as old as the universe, formed within a billion years of the Big Bang. They set a lower limit on the universe's age. It must be at least as old as its oldest clusters. Studying globular clusters reveals galactic history. They remember the early days, when the galaxy was forming. Their orbits trace the halo's shape. Their compositions reveal early enrichment. Metal pore clusters formed from primordial gas, mostly hydrogen and helium. Little else. Metal-rich clusters formed later, from gas enriched by earlier stars. The metal content tells their age. Some globular clusters may be captured. Remnants of dwarf galaxies the Milky Way absorbed. Their stars now orbit our galaxy, prisoners of gravity. The original galaxy destroyed. Only the cluster remains. Omega Centauri is the largest globular cluster, contains millions of stars. It might be the stripped core of a dwarf galaxy, consumed by the Milky Way. Too large to be a normal cluster. Different star populations, multiple generations, Globular clusters are fossils, ancient structures preserved, unchanged for billions of years. While the galaxy evolved around them, they remained constant, time capsules from the early universe. Right now, these clusters orbit, ancient spheres of stars, completing their long elliptical paths, unchanged, eternal, holding billions of years of history, silent witnesses to the galaxy's evolution. Globular clusters orbit the galaxy, so do stars, but galaxies do not rotate like solid objects. Different parts move at different speeds. Near the center, stars orbit fast. Further out, slower. Even further, faster again. The rotation curve is strange, unexpected. This strangeness revealed dark matter. If galaxies were just visible matter, rotation should decline with distance, like planets orbiting the sun. Mercury orbits fast. Neptune orbits slow. Orbital speed decreases outward, but galaxy rotation curves stay flat. Stars at the edge orbit as fast as stars midway out. This should not happen. Not enough visible mass to explain it. Vera Rubin discovered this in the 1970s. She measured rotation curves for many galaxies. All showed the same pattern. Flat curves extending far beyond the visible disk. This meant invisible mass, dark matter, creating extra gravity, holding the outer stars in fast orbits. Without it, they would fly away. The galaxy would disperse. Dark matter exists in halos, spherical distributions surrounding galaxies, extending far beyond the visible matter, 10 times wider than the disk, containing 5 times more mass than all the stars and gas combined. We cannot see dark matter. It does not emit light, does not absorb light, does not interact electromagnetically, only through gravity, its presence inferred from gravitational effects. Galaxy rotation is one effect. Gravitational lensing is another. Massive objects bend light. Dark matter has mass. It bends light passing near galaxies, creates distorted images of background galaxies. By measuring these distortions, astronomers map dark matter, create 3-dimensional maps showing where it concentrates. It clusters around galaxies, forms cosmic structures, but always invisible. What is dark matter? We do not know. Candidates include exotic particles, weakly interacting massive particles, axions, sterile neutrinos, particles predicted by theory but not yet detected. Underground detectors search for dark matter, waiting for a dark matter particle to strike normal matter, create a signal. So far, nothing conclusive. The particles, if they exist, interact too weakly. Dark matter could be primordial black holes, formed in the early universe, not from stars, from direct collapse of dense regions. These would be invisible, provide mass, match observations, or dark matter could be something unexpected. A new type of physics, modified gravity, something we have not imagined. The mystery remains. What we know is dark matter is necessary. Galaxies cannot form without it, cannot hold together without it. The visible universe requires an invisible foundation. This is humbling. Everything we see, stars, galaxies, planets, all made of normal matter, but normal matter is only 15% of the total. The rest is dark, unknown, invisible. Right now, dark matter surrounds you, passing through you, through Earth, through everything. Undetectable, unfelt, but present, providing the gravitational framework, the scaffolding on which the visible universe is built. Galaxies are not isolated. They cluster, group together, held by mutual gravity, creating larger structures. Small groups contain a few galaxies. The local group has about 80 members. The Milky Way and Andromeda are the largest. Dozens of smaller galaxies orbit them. Large clusters contain hundreds or thousands of galaxies. The Virgo cluster has about 1,500 galaxies, 50 million light-years away. The nearest large cluster. In clusters, galaxies move fast, thousands of kilometers per second, orbiting the cluster's center, held by the combined gravity of all members. Most mass in clusters is not galaxies. It is dark matter and hot gas, X-ray emitting gas filling the space between galaxies. This intracluster medium contains more normal matter than the galaxies themselves. The gas is hot, millions of degrees, heated by gravitational compression, by galaxy collisions, by energy from supermassive black holes. It glows in X-rays, visible to X-ray telescopes. Galaxy clusters are the largest gravitationally bound structures. Bigger than clusters, things are not bound. They are expanding with the universe, moving apart. Only clusters remain held together. Superclusters are not bound. They are just regions with many clusters. The Milky Way is part of the Laniakea supercluster, contains about 100,000 galaxies, extends 500 million light-years. But Laniakea is not a structure, not a thing held together, just a designation, a region of space with higher galaxy density. The galaxies within it are drifting apart, carried by cosmic expansion. Clusters themselves are separated by voids, empty regions, few galaxies. These voids are huge, hundreds of millions of light-years across. The universe has structure, clusters and voids, filaments and sheets. This structure formed from initial density variations. Regions that were slightly denser attracted more matter, became clusters. Regions that were less dense emptied out, became voids. Gravity amplified tiny differences, created the cosmic web, the large-scale structure of the universe, visible in galaxy surveys. 3-dimensional maps showing clusters and voids. The structure is still growing. Clusters attracting more galaxies, voids getting emptier, but slowly, the expansion of the universe fights against this, stretching space, moving clusters apart. Eventually, expansion will win. Clusters will separate beyond contact. Each cluster will become isolated, unable to see other clusters. The observable universe will shrink, each cluster alone in expanding space. But this is trillions of years away. Now, clusters remain connected, visible to each other, part of the same cosmic web. Right now, the Milky Way falls toward Virgo, pulled by that cluster's gravity, moving through space, while also moving with the local group toward an even larger concentration, called the Great Attractor. Everything moves. Galaxies orbit in groups. Groups fall toward clusters. Clusters drift through voids, all interconnected, all part of the largest structures in the universe. The Milky Way belongs to a small cluster, the local group, about 80 galaxies in total, spread across 10 million light-years. 2 large spirals dominate, the Milky Way and Andromeda. Both have similar mass, about 1 trillion solar masses each, including dark matter. They are the heavyweights. Andromeda is slightly larger, more stars, brighter, but the difference is small, in the same weight class, true peers. The third largest is Triangulum, a smaller spiral, about 50 billion stars, 10 times smaller than the Milky Way, but still a significant galaxy. The third major member. The rest are dwarfs, small irregular galaxies, or dwarf ellipticals, a few million to a few billion stars. Many orbit the Milky Way or Andromeda, satellites bound by gravity. The large and small Magellanic Clouds are satellites of the Milky Way, visible from the southern hemisphere. irregular dwarf galaxies. The Large Magellanic Cloud has about 30 billion stars. These satellites are being tidally disrupted. The Milky Way's gravity pulls on them, stretches them, strips away their outer stars. Eventually, they will be consumed, absorbed into the Milky Way. Dozens of even smaller dwarfs orbit both galaxies. Ultra-faint dwarfs, containing only a few thousand stars, barely qualifying as galaxies, more dark matter than stars, held together by invisible mass. Discovering these tiny satellites is difficult. They are faint, spread out, blend into the background. Advanced surveys find new ones regularly. The count increases. Why does this matter? Simulations predict thousands of dark matter halos around large galaxies, but we see only dozens of satellite galaxies. The missing satellites problem. Where are they? Perhaps they exist, but are too faint. Too few stars to see. Dark matter, halos with no visible component. Or perhaps dark matter is different than models predict. The mystery continues. The local group has clear boundaries. Beyond about 5 million light-years, galaxies belong to other groups. The nearest large group is the M81 group, 10 million light-years away. Between groups lies mostly empty space, voids, a few isolated galaxies, drifting alone. Most galaxies belong to groups or clusters. Very few are truly isolated. The local group is typical, similar to millions of other groups. 2 large galaxies, several dwarfs. In the grand scheme, nothing special. Just one small corner of the universe. But it is our corner, our neighborhood. These 80 galaxies are the ones we can study in detail, resolve individual stars, map structures, understand formation. Everything we learn about galaxies starts here, in the local group, with the Milky Way, with our nearby neighbors, the laboratory where we understand how galaxies work. Right now, Andromeda approaches. The local group's future is merger. In 4 billion years, the 2 large spirals will collide, combine, create one larger galaxy. The local group simplified. One giant where 2 once existed. Most galaxies are quiet. Stars orbit. Some form, most just exist. But some galaxies are loud, violent, active. Active galactic nuclei are powered by supermassive black holes. Feeding, growing, material spirals into accretion disks, heats up, radiates tremendous energy. The brightest active galaxies are quasars, quasi-stellar objects. They look like stars in images, point sources. But they are distant galaxies. The black hole outshines all the stars. Quasars can be 1 trillion times the sun's luminosity. From a region smaller than the solar system, this energy comes from mass conversion. Matter falling into the black hole converts to energy. E equals mc squared. About 10% of infalling mass becomes energy, far more efficient than fusion. Fusion converts less than 1%. Black holes are the most efficient engines in the universe. Quasars were common in the early universe. When galaxies were young, gas abundant. Black holes fed actively. The sky was full of quasars billions of years ago. Now, quasars are rare. Most galaxies exhausted their central gas. Their black holes starved, went quiet, became dormant like Sagittarius, a star. Occasionally, a galaxy feeds its black hole again. Gas falls inward, from a galaxy collision, from a disrupted star. The black hole activates, briefly becomes a quasar again, then fades. Some active galaxies produce jets, narrow beams of particles accelerated to near light speed. These jets extend thousands of light years, visible in radio waves. When a jet points toward Earth, we see a blazar, extremely bright, variable, flickering on timescales of days or hours. The jet's energy focused directly at us. Radio galaxies have jets perpendicular to our view. We see both jets, extending from the galaxy's center, creating lobes of emission far outside the galaxy. These jets affect their host galaxies, heat the surrounding gas, blow gas out of the galaxy, stop star formation. This feedback regulates galaxy growth, prevents runaway star formation. Seyfert galaxies are mildly active, bright cores, but the galaxy's stars are still visible, less dramatic than quasars, more common today. The Milky Way might have been a Seyfert in the past. All these categories are the same phenomenon: supermassive black holes feeding. The differences are viewing angle and feeding rate. Quasars feed heavily, Seyferts lightly. Blazars point their jets at us. Active galaxies teach us about black holes, about accretion physics, about how matter behaves in extreme gravity. They are natural laboratories, testing physics at limits we cannot recreate. They also serve as beacons. Distant quasars mark the early universe, lighthouses showing where galaxies formed, how structure developed, probes of cosmic evolution. Right now, the nearest active galaxy is Centaurus A, 11 million light-years away. Radio jets extending far beyond the visible galaxy. The central black hole consuming gas, growing slowly, a reminder that even nearby galaxies can be violent. Active galaxies are violent internally, but galaxies also collide, literally. Two galaxies merging, becoming one. Despite being mostly empty, galaxies collide often, in clusters especially. Galaxies orbit. Sometimes their paths cross. Gravity takes over. They merge. The collision is slow, takes hundreds of millions of years. First, the galaxies pass through each other. Gravity distorts both, pulls out tidal tails, long streams of stars stretching between them. The stars do not collide. Too much space between them. They pass through harmlessly, like two swarms of gnats passing. Individual insects do not hit each other, but the galaxy's shapes change. Tidal forces stretch them, pull stars into new orbits, destroy the original structures. Spiral arms disrupted, disks warped. After passing through, the galaxies slow. Gravity pulls them back together. They fall toward each other again, pass through again. This happens repeatedly, each passage mixing the galaxies more. Eventually, they merge completely, become one galaxy, usually elliptical. The collision destroys spiral structure, randomizes star orbits, creates the smooth elliptical shape. The Milky Way will collide with Andromeda. This is certain. They are approaching at 120 kilometers per second. In 4 billion years, they will merge. The collision will not destroy Earth. Our Sun will likely survive, flung to a different orbit, perhaps ejected entirely, sent wandering in intergalactic space, but intact. Stars rarely collide even in mergers. The night sky will change dramatically, Andromeda growing larger, filling the sky. During closest approach, a wall of stars, then separating, approaching again. Years of spectacular views. For civilizations watching, if any remain, it will be the event of their existence. Two galaxies dancing, merging, creating fireworks of star formation. As gas clouds collide and compress, collisions trigger starbursts. Compressed gas collapses rapidly, forms stars at high rates. Both galaxies light up, blue with young, massive stars, briefly brilliant, then fading as the gas is exhausted. The central black holes eventually merge too. They spiral together, orbit each other, and get closer, finally collide, create gravitational waves, merge into one larger black hole. Some collisions are minor, large galaxy consuming a dwarf. The dwarf is torn apart, its stars scattered, eventually absorbed. This happens to the Milky Way regularly. We are eating the Sagittarius dwarf galaxy right now. Tidal streams mark these events, rivers of stars in the halo, remnants of disrupted dwarfs, evidence of past cannibalism. The Milky Way built itself partly through mergers. In the future, more mergers will happen. The local group will consolidate, eventually become one galaxy, Milkomeda, or perhaps something else. The mergers will continue until groups become isolated. Right now, countless galaxies merge, in clusters, in groups, creating ellipticals, triggering starbursts, reshaping the cosmos. Collisions are part of galactic evolution. Natural, inevitable, ongoing. Collisions are dramatic, but galaxies interact without merging. Close passes, tidal forces distorting both, creating beautiful structures. The Whirlpool galaxy shows this, a large spiral with a smaller companion. The companion is connected by a bridge of stars. Tidal interaction pulled the bridge out, stretched between them. The larger galaxy has prominent spiral arms, triggered by the companion's gravity. The companion compressed gas, initiated star formation, made the arms more defined, more beautiful. Galaxies need not touch to interact. Gravity acts at distance. A close pass is enough. Hundreds of thousands of light years apart, still enough to distort. Tidal tails are common, long streams of stars pulled from galaxies. These tails can extend farther than the galaxies themselves. Dramatic evidence of past encounters. The antennae galaxies show tidal tails. Two spirals merging, long arcs of stars stretching outward, like insect antennae, created by tidal forces. Eventually, these tails will fall back, become part of the merged galaxy. Ring galaxies result from head-on collisions, a small galaxy punching through a larger one, creating a ripple, a ring of star formation spreading outward, like dropping a pebble in water. The Cartwheel galaxy is a ring galaxy, the ring perfectly circular, expanding, blue with young stars. The collision happened millions of years ago, the ring still spreading. Polar ring galaxies have rings perpendicular to their disks, created by capturing a smaller galaxy. Tidal forces pulling it apart, its material forming a ring around the larger galaxy. Two structures at right angles. These interactions trigger star formation. Compressed gas collapses, creates new stars. Interacting galaxies often have bright blue regions, active star formation zones, evidence of recent disturbance. Interactions also feed black holes. Gas loses angular momentum, falls toward the center, feeds the supermassive black hole, triggers activity. Many active galaxies show signs of recent interactions. In clusters, interactions are constant. Galaxies pass each other frequently. Tidal stripping occurs. Outer stars pulled away, added to the intracluster light. Diffuse stars between galaxies. Ram pressure stripping also happens. Galaxies moving through hot intracluster gas. The gas acts like wind, blows away the galaxy's own gas, stops star formation, creates jellyfish galaxies, long trails of gas and stars. Even the Milky Way experiences tides, from the Magellanic Clouds, from other satellites. These create warps in our disk, ripples. The disk is not perfectly flat. Tidal interactions bent it. Tidal forces are fundamental. They shape galaxies, trigger evolution, create spectacular structures. Without interactions, galaxies would be simpler, less interesting. Tides add complexity. Right now, tidal forces act throughout the universe. Galaxies pulling on each other, distorting, merging, creating streams and tails. the gravitational dance that shapes galactic structure. Gentle but relentless, always acting. Tidal forces distort large galaxies, but what about small ones? Dwarf galaxies, the universe's most common type. Dwarf galaxies contain a few million to a few billion stars. Small compared to the Milky Way's 200 billion, but they outnumber large galaxies 10 to 1. Most dwarfs are irregular, no organized structure, no spiral arms, no smooth elliptical shape, just random clouds of stars and gas. Chaotic, simple. The Magellanic Clouds are irregular dwarfs, visible from Earth's southern hemisphere, companions to the Milky Way. Eventually, they will be consumed, absorbed into our galaxy. Dwarf ellipticals are smooth, like miniature versions of giant ellipticals. Old stars, no gas, no star formation. Quiet, ancient, often found in galaxy clusters. Dwarf spheroidals are even smaller, fainter, so faint they are nearly invisible, only discovered recently. Extremely low surface brightness, more dark matter than stars. These ultra-faint dwarfs challenge detection. A few thousand stars spread across large volumes. Individual stars barely brighter than background. Special surveys find them. Statistical analysis revealing their presence. Why care about dwarfs? They are common. Most galaxies are dwarfs. Understanding them means understanding typical galaxies, not the spectacular spirals, the ordinary majority. Dwarfs also reveal dark matter. They have the highest dark matter fractions. Some are 99% dark matter, 1% stars, almost entirely invisible mass. This makes them ideal dark matter laboratories. Studying how stars move in dwarfs reveals dark matter distributions, how dark matter clumps, how it interacts with normal matter, or does not interact. The smallest galaxies teach us about the universe's majority component. Dwarf galaxies also preserve ancient chemical signatures. Low mass means less recycling, less star formation. Stars formed early, from primordial gas. Their compositions reveal the early universe. The first stars formed in dwarf-sized dark matter halos, before large galaxies existed. Dwarfs might be fossils from that era, surviving unchanged. Time capsules from cosmic dawn. Some dwarfs are satellites, orbiting large galaxies like the Milky Way. These satellites are common. Each large galaxy has dozens, perhaps hundreds, most undiscovered, too faint to see. The satellite count tests dark matter models. Simulations predict thousands of dark matter halos around large galaxies, but we see only dozens of satellite galaxies. Either most halos have no stars, or dark matter is different than predicted. Field dwarfs are isolated, not satellites, not in clusters, alone in voids. These dwarfs formed in isolation, evolved slowly, undisturbed. They represent pristine galaxy evolution. Blue compact dwarfs are active, bursts of star formation, bright blue stars. Despite low mass, these bursts are triggered by gas infall, or dwarf-dwarf mergers. Brief, intense activity. Dwarf galaxies can merge with each other, create larger dwarfs, or occasionally create spirals. Over billions of years, small galaxies combining, building larger structures. This bottom-up growth. The Milky Way likely formed this way. Many small galaxies merging, growing, eventually becoming the large spiral we see. Dwarfs are building blocks, the fundamental units. Tidal dwarfs form from collisions. When large galaxies merge, tidal tails pull out. Material in these tails can collapse, form new dwarf galaxies, born from debris, short-lived, eventually absorbed. Dwarf galaxies host small black holes, intermediate mass, hundreds to thousands of solar masses. Too small for supermassive, too large for stellar. These intermediate black holes are rare. Dwarfs might be where to find them. Understanding dwarfs completes galaxy knowledge, not just the giants. The full population, from smallest to largest, all part of the cosmic ecosystem. Right now, dwarf galaxies drift everywhere, in clusters, around large galaxies, in voids, mostly invisible, faint but numerous, the majority. The universe's most common galaxy type, small but essential parts of cosmic structure. Dwarf galaxies are mostly dark matter, but they can host life. So can large galaxies, but not everywhere. Some regions are too dangerous. The galactic habitable zone is the region where life can survive long term. Not too close to the center, not too far out. Conditions must be right. Too close to the galactic center is dangerous. Radiation from the supermassive black hole, frequent supernovae, dense star fields where stellar encounters are common. A planet's orbit could be disrupted, ejected from its system. The radiation environment is harsh near the center. When the black hole was active, when it fed heavily, it would have sterilized nearby planets, killed any developing life. Only after it quieted could life survive. Supernovae are also problematic. Massive stars explode, release gamma rays, X-rays, high-energy particles. A nearby supernova could strip a planet's atmosphere, irradiate the surface, destroy life. Near the galactic center, massive stars are common. They live briefly, explode often. A supernova might occur within a few light years every few million years. Too frequent for complex life to develop. Too far from the center is also problematic. Low metallicity, few heavy elements. Planets might not form, or form too small. Without sufficient metals, Earth-like planets are rare. Life needs metals. Carbon, oxygen, nitrogen, iron, calcium, all made in stars, scattered by supernovae. Regions far from the center have fewer metals. First-generation stars. Planets would be different, less hospitable. The habitable zone sits in the middle, about halfway out, where the sun is. Enough metals for planet formation, enough distance from central dangers, safe, stable. This region also has the right star formation rate. Too much, and supernovae are frequent. Too little, and not enough heavy elements. The middle range is optimal. Spiral arms complicate this. When the sun passes through an arm, supernova risk increases. Star formation is active there. Massive stars present. But passages are brief, a few tens of millions of years. Then back to quieter inter-arm space. Earth has existed 4.5 billion years, passed through spiral arms many times, survived each passage. Perhaps the risk is not as high as feared, or perhaps we were lucky. The habitable zone concept applies to galaxies too, not just planets around stars. Some galaxies are more habitable than others. Spirals better than ellipticals. Ellipticals have no ongoing star formation, no new planetary systems. Small galaxies might be too unstable, easily disrupted by neighbors. Mergers common. Large galaxies might be too violent. Too many supernovae. Intermediate mass is best. The Milky Way is a good size. Large enough for stability. Metal rich enough for planets. Not too violent. A habitable galaxy. This affects the search for life. Where to look? Planets around stars in the galactic habitable zone. In galaxies like the Milky Way. Similar metallicity. Similar activity level. SETI searches focus on nearby stars. Most are in the habitable zone. Similar conditions to Earth. If intelligence is common, this is where it should be. Of course, life might adapt to different conditions. Survive where we think impossible. Our definition of habitable might be too narrow. Life might exist in ellipticals, near galactic centers, in dwarfs. We do not know. But if life is like Earth life, if it needs similar conditions, then the galactic habitable zone matters. It defines where to search, where planets might harbor complex life. Right now, the Sun orbits in this zone, safe distance from the center, safe distance from the edge, in a region where life could develop, did develop, where you exist, in the right place, at the right time. The galactic habitable zone affects life, but all galaxies are observable, even the most distant. Light travels, eventually reaches us, tells stories. The farther away a galaxy, the longer light takes to arrive. Andromeda is 2.5 million light-years away. Its light is 2.5 million years old. We see its past. Very distant galaxies show us the early universe. Light from 10 billion light-years away, left when the universe was young, only 3 billion years old. Those galaxies look different. They are smaller, less organized, more irregular. Star formation is rapid, blue colors everywhere. Young massive stars dominating. Not like modern galaxies. The Hubble Space Telescope photographed deep fields, tiny patches of sky, long exposures. Thousands of galaxies appear, each one distant, ancient, showing cosmic history. The farthest galaxies are red shifted, their light stretched by cosmic expansion. Blue light becomes red. Red becomes infrared. The James Webb Space Telescope sees infrared, specifically designed for distant galaxies. Webb has found galaxies from 400 million years after the Big Bang. Tiny, compact, actively forming stars. These are the first galaxies, building blocks of everything that came later. Observing distant galaxies is time travel. We see the past, directly, not inference, not theory. Actual light from billions of years ago, showing how galaxies were then. By comparing distant and nearby galaxies, we trace evolution, how spiral galaxies formed, when ellipticals became common, how star formation changed over time. The cosmic history of galaxies. Distant galaxies are also extremely faint, their light diluted by vast distance, spread across expanding space. Advanced telescopes are needed, large mirrors, long exposures, sensitive detectors. Gravitational lensing helps. Massive galaxy clusters bend light, act as natural telescopes, magnify background galaxies, make faint objects visible. This reveals galaxies too distant to see otherwise. Some distant galaxies appear multiple times, lensed into arcs, multiple images of the same galaxy, seen from different paths around the cluster. These multiple images allow detailed study. Spectroscopy reveals galaxy properties, break light into spectra, measure wavelengths, determine redshift, chemical composition, star formation rate, all from analyzing light. Distant galaxies are moving away. Cosmic expansion carries them. The farther they are, the faster they recede. This is Hubble's law, velocity proportional to distance. The most distant galaxies recede faster than light, not through space. Space itself expands. Their light barely reaches us, stretched enormously, redshifted into infrared, even microwave, eventually radio. There is a distance we cannot see beyond, the cosmic horizon. Light from farther has not reached us yet. The universe is only 13.8 billion years old. Light has had that long to travel. We see a sphere of that radius. Beyond the horizon, more universe exists. We cannot see it, cannot observe it. It is causally disconnected. Those regions will never affect us. We will never affect them. But within the horizon, all galaxies are observable, in principle, with large enough telescopes, long enough exposures, We can map the observable universe, see all galaxies within reach. This is being done. Surveys mapping millions of galaxies, creating three-dimensional maps, showing cosmic structure, where galaxies cluster, where voids lie, the large-scale pattern. Right now, distant galaxies send their light toward us, from billions of years ago, traveling through expanding space, arriving tonight, captured by telescopes, telling us about the cosmos, about how we got here. Distant galaxies appear different, but all galaxies have colors. These colors reveal their nature, their histories, their future. Blue galaxies are actively forming stars. Massive blue stars dominate, hot, bright, short-lived. Their presence means recent star formation, ongoing activity. Red galaxies have stopped forming stars. Only old red stars remain. Red giants, red dwarfs, no young blue stars. These are retired galaxies, living on past glory. The color magnitude diagram shows this. Plot galaxy brightness versus color. Two populations emerge. Blue cloud, red sequence. Most galaxies fall in one or the other. The blue cloud contains spirals, irregulars, dwarf galaxies actively forming stars. These are the factory galaxies, still working, still creating. The red sequence contains ellipticals, S0 galaxies, old spirals that exhausted gas. These are finished. No more raw material, just aging stars. Between the populations lies the green valley, galaxies transitioning from blue to red, star formation declining, gas running out. This transition is rapid. Relatively few galaxies caught in the act. What causes the transition? Several things. Mergers disrupt gas, stop formation. Ram pressure stripping in clusters removes gas. Active galactic nuclei heat gas, blow it away. Once star formation stops, galaxies redden quickly. Massive blue stars die within millions of years. Only red stars remain. The color change is fast. Astronomically speaking, environment affects colors. Cluster galaxies are mostly red. Field galaxies often blue. Clusters are violent. Interactions common. Gas removed, star formation stops. The fraction of blue versus red galaxies has changed over time. Early universe had more blue galaxies. Star formation was higher. Now, more galaxies are red. The universe is aging. Eventually, all galaxies will be red. Star formation will stop everywhere. Gas will be exhausted, or too hot. Only old red stars will remain. The universe will fade. But this takes trillions of years. Now the universe is still vibrant, still forming stars, still creating new populations. The transition ongoing. Infrared observations reveal hidden star formation. Dust obscures blue light, makes galaxies look red. But infrared penetrates dust, shows star formation hiding inside. Some red galaxies are dusty, still forming stars, just hidden. These dusty star-forming galaxies are common at high redshift. In the early universe, building massive ellipticals, ultraviolet observations reveal the hottest stars. Very massive, very short-lived. Their presence indicates very recent star formation, within the last million years. Combining observations across wavelengths gives complete pictures. Infrared for dust, obscured formation. Visible for overall light. Ultraviolet for recent activity. Each wavelength tells part of the story. Galaxy colors evolve over billions of years. Blue galaxies become red. The fraction shifts. The universe transitions from active to passive, from factories to museums. Tracking this evolution reveals how galaxies die, how star formation ends, what triggers the change. When it happens, the process that turns vibrant spirals into quiet ellipticals. Right now, galaxies span all colors: blue, green, red. each color a stage, a moment in galactic life, from birth through maturity to old age. The spectrum of galaxy evolution, all visible, all teaching us how galaxies live and die. Galaxy colors reveal individual histories, but galaxies are not isolated. They form patterns, large-scale structures, the cosmic web. On small scales, galaxies cluster, groups, clusters. On larger scales, these clusters connect, form filaments, long chains of galaxies, stretching across hundreds of millions of light years. Between filaments lie voids, vast empty regions, few galaxies. These voids are enormous, often larger than the filaments. Most of space is void. The cosmic web resembles foam, thin sheets and filaments outlining empty bubbles. Galaxies concentrated on the surfaces, voids inside. This pattern repeats across the observable universe. This structure formed from quantum fluctuations. In the early universe, tiny density variations, amplified by inflation, grown by gravity over billions of years. Denser regions attracted matter, became filaments, became clusters. Less dense regions emptied out, became voids. Gravity created structure from almost nothing. The structure is hierarchical. Small clumps merge into larger ones into larger still. Bottom-up growth, from tiny fluctuations to cosmic web, over 13 billion years. Simulations reproduce this structure. Start with initial fluctuations. Apply gravity. Let dark matter evolve. The cosmic web emerges naturally, matches observations, validates our understanding. Normal matter follows dark matter, falls into dark matter halos, forms galaxies where dark matter concentrates. The visible web traces the invisible dark matter web. Galaxy surveys map this structure, measure millions of galaxy positions. Redshifts create three-dimensional maps, show filaments, voids, the full web. The largest structures are barely visible, so large they span significant fractions of the observable universe. These structures are young, still forming, still growing. One example is the Sloan Great Wall, 500 million light-years long, the largest known structure, a concentration of galaxies, a massive filament. But even this is not a thing, not held together, just a region where matter is denser. The galaxies within it do not know they are part of a wall. Each follows its own path. The cosmic web defines large-scale structure. Above clusters, structure is statistical, not gravitationally bound, just density variations, regions with more or fewer galaxies. Understanding the web reveals dark matter distribution, dark energy effects, how the universe evolved. Large-scale structure constrains cosmology. The web also affects galaxy evolution. Galaxies in filaments differ from those in voids. More interactions in filaments, more mergers, different star formation histories. Void galaxies are isolated, undisturbed, evolve peacefully, often blue, still forming stars, no neighbors to interact with. Filament galaxies collide, merge, trigger starbursts, or have gas stripped, become red. Environment shapes galaxy evolution, even on these large scales. The cosmic web is the universe's skeleton, the structure all smaller things fit into. Galaxies fill nodes and filaments. Voids create empty spaces, all interconnected, all part of one giant pattern. This pattern is beautiful, elegant, repeated across space. Wherever we look, the same structures, filaments, voids, clusters, the universe self-similar at large scales. Right now, the cosmic web stretches across space, connecting galaxies across billions of light years. The largest pattern in existence, invisible except through galaxy positions. The framework underlying everything, the the structure of the cosmos. The cosmic web exists now, but everything changes. Galaxies evolve, merge. The future will be different. Cosmic expansion continues, accelerates. Dark energy drives it. Space expands faster over time. Eventually, this separates all structures. Within galaxy clusters, galaxies remain bound. Gravity holds them together. Despite expansion, clusters are permanent, will not disperse, but clusters will separate from each other. Already happening, accelerating. Eventually, each cluster will be alone, isolated, unable to see other clusters. The observable universe will shrink. From each cluster's perspective, first distant clusters disappear, redshifted beyond detection. Then closer ones. Eventually, only the local cluster remains visible. In trillions of years, a civilization in our cluster will see no other galaxies, just our merged local group. Everything else expanded beyond the cosmic horizon. Invisible, gone. Within clusters, mergers continue. Galaxies collide, combine. Eventually, each cluster becomes one giant elliptical, all smaller galaxies consumed. One massive galaxy remaining. The Milky Way and Andromeda merge in 4 billion years. This is just the beginning. Other local group galaxies will merge too, eventually creating one large elliptical, Milkomeda or beyond. Star formation will stop. Gas will be exhausted, or heated, or ejected. No new stars, only existing stars aging, dying, the galaxy fading. Red dwarfs will dominate. These stars live trillions of years. After all massive stars die, only red dwarfs remain. The galaxy will be dim, red, filled with dying stars. Eventually, even red dwarfs die, become white dwarfs, cold, dark, slowly cooling. The galaxy becomes invisible, just dark remnants orbiting. White dwarfs cool over trillions of years, eventually become black dwarfs, objects that do not exist yet. The universe is too young. Not enough time has passed. Brown dwarfs will remain, failed stars, never hot enough to fuse, just slowly cooling, drifting through dark galaxies. Black holes will be the last major objects. Stellar black holes, supermassive ones. They evaporate through Hawking radiation, but this takes impossibly long. 10 to the 100 years, unimaginable time. Protons might decay. This is theoretical, not observed. But if they do, even white dwarfs will dissolve. Matter itself unstable. Only black holes remaining. In the extreme far future, the universe is cold, dark, expanded beyond recognition. Each galaxy cluster isolated, containing one massive dead galaxy. No stars, no light, just black holes evaporating into nothing. This sounds bleak, but it is trillions of years away. Now the universe is young, active. Galaxies merge, stars form, everything dynamic. The future is certain only in broad strokes. Details remain unknown. Perhaps civilizations will intervene, harvest stars, move galaxies, prevent some evolution. Perhaps new physics will be discovered, changes our understanding, makes different futures possible. We only know physics as we understand it now. What is certain is change. Galaxies are not eternal. They evolve, merge, eventually die. Nothing is permanent. Everything transforms over time. Right now, we live in a special era, when galaxies are visible, when stars form, when the universe is interesting. This epoch will not last forever, but it is now, and that is something. The future is distant. The present is here. You, now, in this galaxy, this moment. You live in a spiral galaxy, one of hundreds of billions, in a universe of trillions. Your galaxy is not special, not unique, but it is yours. The Milky Way is 100,000 light years across. contains 200 billion stars. Your sun is one, average, unremarkable, halfway out from the center, in a minor spiral arm. But this average star hosts a planet with life, with consciousness, with you. This makes it special. Not to the galaxy. The galaxy does not know, does not care, but to you, your world, your life. Every atom in your body was made in stars, carbon in stellar cores, oxygen in massive stars, iron in supernovae. You are made of galaxy, literally, recycled stellar matter, star stuff. The galaxy created you through billions of years of evolution. Stars forming, dying, enriching gas, creating heavier elements, eventually planets, eventually life, eventually you. You are the galaxy's way of knowing itself. Through your eyes, the galaxy sees. Through your mind, it understands. You are consciousness emerging from stellar matter. Look up at night. The stars you see are neighbors. The same galaxy, the same structure you belong to. You are inside, part of it, not separate, connected. If this journey through galaxies has brought you wonder, if these facts have helped you find calm, I would be grateful if you subscribed. This community explores the cosmos together, finding peace in understanding. Leave a comment about what amazes you most about galaxies. What questions you still have. I love knowing we are here together, learning, wondering, connected across distance by shared curiosity. Billions of people look up at the same stars, from different places, different times, but the same galaxy, the same sky. We are all galactic citizens, sharing this structure, this home. The Milky Way will be here long after you, will be here long after humanity. It existed billions of years before Earth formed, will exist billions of years after Earth is gone. This is humbling. Your life is brief, a moment, but you are part of something ancient, something vast, something that continues. The galaxy flows through time. You are one wave in that flow, and there is peace in this. You are not the center. The galaxy does not revolve around you. You are small, temporary, insignificant in cosmic terms. But you exist. You are here, now, conscious, aware, able to understand, to appreciate, to look up and know what you see, to know where you are, what you are part of. Tonight, the galaxy rotates. Stars orbit, gas collapses, new stars ignite, black holes feed, mergers happen somewhere, all the processes continuing, as they have, as they will, and you are here, in this moment, in this galaxy, alive, aware, part of it all, connected to every star through gravity, through shared origin, through the simple fact of being here, together, in the Milky Way, our galaxy, our home. Sleep peacefully, knowing you belong to something immense, something ancient, something beautiful, the galaxy that carries you through space, through time, always.